Welcome back to the Deep Dive. Today we are tackling something really critical, conditions often called blue baby syndrome.
hmm
We're specifically diving into cyanotic congenital heart diseases.
Right. These are heart conditions where fundamentally the body just isn't getting enough oxygenated blood. The underlying issue is usually a structural one, what we call a right-to-left shunt.
Okay, right to left shunt. For those of us maybe not deep in cardiology daily, what does that actually mean for the baby?
Yeah, good question. So think of the heart having two sides, right? The right side gets the blue blood back from the body, the deoxygenated stuff. That should go only to the
Fully
lungs.
oxygenated.
Exactly. Then the left side gets that red oxygen-rich blood from the lungs and pumps it out to the body. A right-to-left shunt is basically a leak or maybe a wrong turn.
Like a plumbing mistake.
Pretty much. It lets that blue deoxygenated blood bypass the lungs entirely and mix directly into the blood going out to the body.
Ah, so the body gets this mix of blue and red blood, leading to that characteristic cyanosis, that bluish tint. And today, our mission really is to show how three major, pretty scary defects,
Tetralogy of Fallot, transposition of the great arteries, and persistent truncus arteriosus.
that these three actually share a single origin point, a specific failure way back in early development.
That's the key. They're all conotruncal defects. Understanding that common root makes grasping these complex conditions honestly a lot easier.
Okay, let's unpack this by looking at the heart's original blueprints.
So the critical window we're talking about is really early, weeks 4 to 8 of pregnancy. At this stage, the developing heart has just one big pipe leading out of it, the truncus arteriosus.
One exit pipe for everything.
Initially, yes. And that single pipe has to be divided, perfectly partitioned and twisted into the two main arteries, the aorta for the body and the pulmonary trunk for the lungs.
So who does the building? Who's responsible for splitting that pipe correctly?
That job falls to a really special group of cells called neural crest cells. You can kind of think of them as the specialist engineers or the construction crew for this specific job.
Okay.
They migrate into the heart region and are responsible for forming the wall, the divider, called the aorticopulmonary septum. It's this septum that does the twisting and dividing. If these cells don't show up, or if they build the wall wrong, the whole outflow system is compromised.
And this isn't just a heart thing, is it? If these neural crest cells have problems migrating, it affects other areas too.
Exactly right. And that's where this connection becomes really high yield clinically. Problems with neural crest cell migration are often linked to a specific genetic issue, the 22q11 deletion, sometimes called DiGeorge syndrome.
Oh, yeah.
And those same neural crest cells, they don't just build the heart septum. They're also crucial for developing structures in the neck and face, like, importantly, the thymus gland.
Which is key for the immune system.
Right, T cells specifically, and also the parathyroid glands.
Which control calcium levels. So,
Also,
hang on. A single problem with these migrating cells could cause a major heart defect and immune problems and calcium issues.
that's precisely it. So if you see a baby with one of these severe conotruncal heart defects, you absolutely need to think about potential T cell deficiencies leading to infections and hypocalcemia, low calcium, maybe even seizures in a newborn, because the parathyroids might also be affected. It's all connected back to that early developmental glitch.
Wow. Okay, so that really reframes these heart defects. They're not isolated events, but maybe different outcomes depending on how that septum construction failed. What are those main failure modes?
It boils down to 3 basic ways the build went wrong, which is super helpful for remembering them. 1, the septum gets built, but it's malaligned, sort of crooked or off-center. That leads to tetralogy of Fallot.
Okay, crooked wall.
2, the septum forms, but it fails to do its crucial spiral or twist, it just goes straight. That results in transposition of the great arteries, TGA.
Straight wall, wrong connections.
And 3, the builders, the neural crest cells, essentially don't show up properly, and the septum is just absent. It never forms. That gives you persistent truncus arteriosus, PTA.
No wall at all. Got it.
Yeah.
Malaligned, non-spiral, or absent.
All right, let's start with tetralogy of Fallot, or TOF. It's actually the most common cyanotic heart defect you'll see, and the core issue here is that malaligned septum. It's shifted, typically pushed forward and over towards the right side.
Okay, so the wall's just built in the wrong spot.
Yeah.
But how does that one single misalignment cause 4 distinct problems? That's the tetralogy part, the four things, right? The prove mnemonic.
Yeah, exactly. It's a domino effect. Because the septum is shifted forward and to the right, it doesn't divide the outflow tract evenly. The part that's supposed to become the pulmonary artery ends up too small, too narrow. That's pulmonary stenosis, the P, improve. Basically, it obstructs blood flow out of the right ventricle.
Okay, so that's the first domino.
Right. Now, because the right ventricle is pumping against this narrowed exit, it has to work much harder. Over time, the muscle thickens. That's right ventricular hypertrophy, or RVH, the R.
Makes sense. Increased workload leads to bigger muscle.
Then, because the septum is misplaced, it doesn't line up correctly with the lower part of the heart, the ventricular septum. This leaves a hole between the ventricles, a ventricular septal defect, or VSD, that's the V.
Oh.
And finally, because the septum is shifted, the aorta doesn't sit neatly over the left ventricle where it should. It ends up straddling that VSD, sitting partially over the right ventricle too. We call that an overriding aorta, the O, so PROV, all stemming from that initial malalignment.
That's actually quite logical when you lay it out like that. And you said the pulmonary stenosis is really the main driver of how blue the baby gets.
Absolutely critical. The severity of the pulmonary stenosis dictates everything. If that exit to the lungs is really tight, the pressure builds up in the right ventricle, and the path of least resistance for that blue blood becomes
shunting across the VSD into the overriding aorta. The right to left shunt.
Exactly. More stenosis means a bigger shunt, means more cyanosis.
And visually, that RVH, the thickened right ventricle, can actually change the heart shape on an X-ray, right? That classic boot-shaped heart.
That's the one. The enlarged RV lifts the apex of the heart up. But clinically, the really dramatic thing you hear about is the TET spell.
Right. These sudden episodes where the baby becomes intensely blue and breathless. Scary stuff.
Terrifying for parents, often triggered by crying, feeding, or any kind of exertion. But here's the fascinating part, the squatting reflex.
Yes. Why does squatting, or pulling the knees to the chest, actually help? It seems so counterintuitive for a heart problem.
It's pure mechanics. Really brilliant, actually. When a child squats, or when you put them in that knee-chest position, it kinks the big arteries in the legs and increases pressure in the lower body dramatically. This instantly jacks up the systemic vascular resistance, or SVR.
Okay, SVR goes up. That's the resistance the left ventricle has to pump against to get blood out to the body. How does making the left side work harder help the right side?
Because it changes the pressure dynamics across that VSD. Remember, before squatting, the relatively lower pressure in the aorta made it easy for blue blood to shunt right to left. But when you suddenly crank up the SVR, you increase the pressure on the left side.
So now the path of least resistance changes.
Precisely. Suddenly, it's relatively easier for the right ventricle to push blood through that narrowed pulmonary valve towards the lungs, rather than shunting it across the VSD into the now high-pressure aorta. You're essentially forcing more blood to take the correct path to the lungs, temporarily improving oxygenation. It's a clever physiological trick. Okay, next up, transposition of the great arteries, TGA. This is our non-spiral fate. The neural crest cells did their job, they formed the septum, but it didn't execute that crucial twist as it divided the truncus.
So instead of the pulmonary artery and aorta crossing over each other as they leave the heart, they just run straight up, parallel, and they're connected to the wrong ventricles.
Exactly. The aorta mistakenly comes off the right ventricle, and the pulmonary artery comes off the left ventricle. Complete switcheroo.
Physiologically, that sounds catastrophic. What does that actually do to blood flow?
It creates two completely separate parallel circuits. Think about it. Blue blood comes back from the body to the right ventricle.
And gets pumped right back out to the body via the misplaced aorta. Never goes to the lungs.
Correct. Meanwhile, red oxygenated blood comes back from the lungs to the left ventricle.
And gets pumped right back to the lungs via the misplaced pulmonary artery. Never gets to the body.
Right. So you have blue blood circling the body and red blood circling the lungs. They never mix naturally.
Which means profound cyanosis right from birth. Like immediately.
Yes. Severe, deep cyanosis, usually apparent within hours, sometimes minutes of birth. And critically, this is cyanosis that does not improve with supplemental oxygen.
Why not? If the lungs are working and getting oxygen.
Because the oxygenated blood is trapped in the lung left heart loop. Giving more oxygen just makes the blood looping back to the lungs even redder, but it still can't reach the body where it's needed. The problem isn't the lungs, it's the plumbing.
Okay, that makes sense. And the X-ray finding here is different too, right? Not boot-shaped.
No, because the great vessels aren't crossing. The base of the heart, the mediastinum, looks unusually narrow on X-ray. This gives the classic egg on a string appearance. The egg is the heart, and the string is the narrow superior mediastinum.
So if these circuits are totally separate, how does the baby survive even for a short time?
Survival is entirely dependent on some kind of connection, a shunt, between the two circuits that allows some mixing of blue and red blood. Usually this means relying on the fetal connections that haven't closed yet.
Like the patent ductus arteriosus, PTA, between the aorta and pulmonary artery, or the patent foramen oval, PFO, between the atria.
Exactly. Those have to stay open to allow a little bit of oxygenated blood to reach the body and a little deoxygenated blood to reach the lungs.
He explains the urgency. You need that mixing. So keeping the PDA open is priority number one.
Absolutely. As soon as TGA is suspected, you start an infusion of prostaglandin EO. That's a medication that keeps the ductus arteriosus patent, keeps it open. That buys time.
Buys time for what?
Buys time to stabilize the baby and get them to surgery for the definitive repair, which is usually the arterial switch operation, where they literally cut the great arteries off and switch them back to the correct ventricles. It's a race against the clock from delivery. All right, our third and final fate, persistent truncus arteriosus, or PTA. This is the most fundamental failure of the three. This is the absent septum scenario. The neural crest cells basically failed to show up and build that dividing wall at all.
So no aorticopulmonary septum, meaning there's just one single large artery leaving the heart instead of two.
That's exactly it. One common arterial trunk arises from both ventricles, and it supplies blood to the systemic circulation, the body, the pulmonary circulation, the lungs, and often the coronary arteries too, all from this single vessel. Complete mixing.
One pipe out for everything.
Yeah.
And you mentioned a rule here. Something about VSDs.
Yes, there's an absolute association. PTA always occurs with a large ventricular septal defect. You cannot have PPA without a VSD.
Why is that?
Because the final closure of the hole between the ventricles, the ventricular septum, actually requires the proper formation and alignment of the outflow tract septum, that aorticopulmonary septum. If the outflow septum is absent, that final piece of the ventricular wall can't form properly, leaving a large VSD underneath the single trunk. Structurally inseparable.
Okay, got it. So what are the consequences of having this one big pipe feeding both the body and the lungs? Where does the blood mostly go?
Well, that's the main problem. Blood will always follow the path of least resistance. And the pulmonary circulation, the lungs, is naturally a much lower pressure, lower resistance circuit compared to the systemic circulation.
So the lungs get flooded.
Massively flooded. Because that single trunk is pumping blood out at high systemic level pressure, a huge proportion of that mixed blood gets shunted directly into the low resistance pulmonary arteries. We call this pulmonary overcirculation or pulmonary plethora.
Like opening a fire hose into a garden hose system. That sounds really bad for the lungs and the heart.
It is. It leads to symptoms very quickly.
Yeah.
So babies with PTA have cyanosis because the blood is mixed, but they very rapidly develop signs of severe heart failure, difficulty breathing, poor feeding, sweating, usually within the first few weeks or months of life. It's driven by that relentless volume overload on the lungs and consequently the heart.
And connecting back to the beginning, this complete failure, the absent septum, this one has a particularly strong link to that neural crest problem, the 22q11 deletion.
Yes, the association between PTA and 22q11 deletion, DiGeorge syndrome, is very strong. It represents perhaps the most severe end of the spectrum of conotruncal defects caused by faulty neural crest cell migration. #outro.
So what does this all mean when we pull it all together?
I think it means that when you're faced with these conditions, 2, TGA, PTA, which can seem really complex and daunting, you don't actually need to memorize 3 totally separate problems. You just need to ask one question. What went wrong with the aorticopulmonary septum?
Right. How did those neural crest cell builders mess up?
Exactly. Did they build it, but it was malaligned, crooked? That's 2TF. Did they build it, but it was non-spiral straight? That's TGA. Or was it simply absent altogether? That's PTA.
It really highlights that these aren't just random developmental accidents. They're logical consequences of specific failures in that early construction plan.
Yeah.
And I think what's really striking, as you mentioned earlier, is how far-reaching the consequences of that single type of cellular failure can be.
Absolutely. Which brings us back to that 22q11 deletion and the handy mnemonic often used for it, CAT-CH22.
CH22. Let's break that down.
Right. So C is for cardiac defects, primarily the conotruncal ones we've just discussed. A is for abnormal facies, characteristic facial features. T is for thymic hypoplasia or aplasia.
Leading to the T-cell deficiency and immune problems.
Yep. The second C is for cleft palate, and H is for hypocalcemia or hypoparathyroidism due to the parathyroid glands failing to develop properly.
Wow. Cardiac abnormal facies, thymus, cleft palate, hypercalcemia, all potentially stemming from that one issue with neural crest cell migration linked to that spot on chromosome 22.
It really underscores that a single error in the body's early blueprint affecting just one type of cell doesn't necessarily stay localized. It can ripple outwards, impacting multiple, seemingly unrelated systems, the heart, the immune system, calcium balance, even facial structure.
So the provocative thought maybe for you, our listeners, is this. When you encounter any kind of developmental or structural defect, especially one appearing early in life, it's worth considering. Could this be just one manifestation of a broader issue in those fundamental embryonic building blocks? What other systems might share that same developmental origin?
It forces you to think systemically right from the start. The heart is never truly built in isolation.